Terus kalau masuk Cititation, wah anjing, sesi induction cuma 2 menit paling. Itu akan videonya dari videonya dari potongan benar.
Itu buku tadi ngomong di masyarakat.
Wah, udah.
Oh, expected.
Bilang kok enggak. Ini aku darinya.
Yes, please.
Lagu piano. Iya, lagu piano. Tapi Ini kamu duduk dulu. Ready. Ini.
Ladies and gentlemen, the opening program will commence shortly. Before we begin today's event, we would like to conduct a safety induction. We are currently in the auditorium on the third floor of Smart Green Learning Center building. The exit will be on the left and right side of the stage. Please head south to reach the emergency stairs.
In case of fire or earthquake, strictly use the stairs. Do not use the elevators. Everyone must evacuate the building and go to the designated assembly point.
Good morning, ladies and gentlemen. Very warm greetings to each and every of you.
Welcome to the 5th ICEDM Consortium Workshops Plenary Session Day 2.
I am Haston Abilah Pribadi and my partner
Nikita Sekarkinanti,
as the Master of Ceremony for this event session.
on behalf of the organizing committee, we extend our appreciation for your presence today.
His Excellency Professor Koichi Kusunoki, Secretary General International Association for Earthquake Engineering.
Dean Faculty of Engineering UGM, Professor Insinyur Selo, Bachelor of Engineering, Master of Engineering, Master of Science, Doctor of Philosophy. Head of Civil and Environmental Engineering Department, Professor Insinyur Tengku Faisal Fatuni, and the Chairman of the 5th ICEDM, Professor Insinyur Bambang Suhendro, Master of Science, Doctor of Philosophy, and to all of our keynotes.
We would like to thank you for participating in our event, for being our sponsorship. Adikarya, Wika Beton, Geotekindo, Jaya Konstruksi, Sumitomo Rubber, Jasa Marga. Thank you very much for your sponsorship, cooperation, and understanding in making for our event a grand success. On this special day, we will have several agenda, and before the session begins, allow us to read it.
First, this session will begin with the opening ceremony. Second, there will be a photo session.
Third, we will have our first plenary session, and the last but not least, we will have the second plenary session and end it with break and lunch. As we previously mentioned before, first we will have opening ceremony by Professor Iwayan Sengara.
So without further ado, let us now begin by welcoming the President of the Indonesian Earthquake Engineering Association. Please welcome Professor Iwayan Sengara.
Good morning to all participants of the 5th International Conference of Earthquake Engineering. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera buat kita semua. Om Swastiastu. Salam kebajikan, namo buddhaya. Well, on behalf of the Indonesian Earthquake Engineering Association, ARGI, it is our pleasure to welcome you again in this second day of our conference. So all the participants who are attending here offline in this room, so who are mostly attending online, thank you for your participation. This has been the 3 years passed after the 4th International Conference of Earthquake Engineering in Padang in 2019. That was before the pandemic. And we are surprised now that the number of participants during this conference is double, because including online, some over 1,000. Previously, we have maybe around 400, 500 participants. ARGI basically organization committed to contribute in disaster risk reduction related to earthquake and tsunami risk. One of many ways to actively promote this effort is to gather various stakeholders together to sit, to share, to listen, and to discuss to the recent findings in the earthquake engineering technology and disaster mitigation as what we now experience. So this 5th International Conference on Earthquake Engineering and Disaster Mitigation is a venue to achieve this goal. We are pleased that ARGI can maintain to regularly organize this conference since the first international conference in Jakarta in 2008. Yeah, we have organized this conference periodically every 3 years. This has becoming reality because of your participation. So at this opportunity, I would like your participation to join ARGI as a member who are not a member yet, to participate as a member, and you can go to our website www.rgi.org, and we will welcome to register and join ARGI as a member. So in line with this conference, ARGI would like to keep updated and would like your participation to be together to reduce earthquake disasters through various related activities and development work to promote earthquake and tsunami resistant design and construction of housing infrastructures and all of the development in Indonesia. Of the framework for disaster risk reduction and the 2030 United Nations Agenda for Sustainable Development. So if you recall, well, it's a development on various aspects of earthquake risk reduction. Also, if we recall, within the Asian region countries, there has been an Asian minister meeting on disaster management, AMMDM, back in 2015, promote the Asian vision for disaster risk reduction to 2025. So now we are in the 2020. So what we expect is we contribute in whatever we need to contribute in the 2025 ASEAN ministerial meeting, the ASEAN Vision. And recently, on May 23 to 28 May 2022, we have Indonesia has hosted a global platform for earthquake disaster reduction, not only earthquake but the disaster risk reduction (GPDRR) in Bali. And Indonesia has released what we call Bali 22. So I would like to invite you through this conference and with the coming activities together support all of this. Today, the conference yesterday has been successful, keynote, and to be interesting and fruitful. Today, I believe thank you for all the speakers. Particular thank to Professor Koichi Kunoki as the Secretary General of the International Association for Earthquake Engineering. RG has been an active member of and participate in periodic world conference and to have agreement engineering association, and we have signed that. Well, thanks also to all the speakers and all the participants for your contribution to attend this conference. For us, RG, by participating in this conference, you have indirectly contributed in the effort of this reduction. Then you will be the actors that have knowledge, and the knowledge with the commitment in your profession as engineers, researchers, and managers are actually the leader for disaster risk reduction. Well, today there will be several keynote papers to be presented by distinguished speakers. Professor Tony Young from University of British Columbia, Canada. Professor Hitoshi Tanaka from Tohoku University. Professor Kazuo Konagai from University of Tokyo, and Professor Junji Kyono from Kyoto University, and also the president of the JAEE. And later, Professor Rajiv Sao from Keio University, Japan, and Professor Krishna as pribadi from ITB. Well, thank you all for your opportunity and your valuable contribution to this conference. Well, finally, on behalf of our association, I deeply appreciate all the hard work of Gajah Mada University and the Daerah Istimewa Yogyakarta chapter of Indonesian Association for Earthquake Engineering for organizing this conference as host. So great appreciation to Professor Bambang Suhendro. I also would like to appreciate all the members of the committee, and I would like you to join, give applause to Bambang Suhendro. Well, I would like also you to appreciate RG Executive Committee, Dr. Made Swarjana is here, Dr. Diah Kusumastuti, I think is also here, and Dr. Ridolfa and Dr. Erwin Lim for continued support to RG and to this conference and previous conferences. To end my opening remarks, once again, thank you to all participants for attending this conference. I would like you to join us. Let us together build back better. Let's together contribute to quick disaster risk reduction. Have a enjoyable and fruitful conference. Bless all of you. Thank you.
Wow, it was amazing opening from Professor Iwayan Sengara.
Indeed, ladies and gentlemen, let us give appreciation and a round of applause for Professor Iwayan Sengara.
Before we move on the next agenda, we will first have a photo session with the audience here and the platform. So please, ladies and gentlemen, please stand please. Let's begin. Thank you so much. Please have your seats.
On to the next session. For the main agenda in today's session, we will have plenary session. This session will be divided into two. The moderator for the first session is Professor Yoyong Arfiadi. He is a professor in Atmajaya University, Yogyakarta. And he has an expertise in structural engineering. Therefore, please welcome Professor Yoyong Arfiadi.
Okay, thank you. Good morning, ladies and gentlemen. So we will continue our conference today. At this second day of the plenary session, we have three keynote speakers. The first one is Professor Tony Young from University of British Columbia, Canada. And the second is Professor Hitoshi Tanaka from Tohoku University, Japan. And the second one is Professor Kazuo Konagai from University of Tokyo, Japan. I would like to check whether Professor Tony Young has already joined us here. Professor Tony Young?
Yes, I'm here.
Are you with us?
Yes, I am here. Can you hear me well? Yes, I'm here.
Okay, great. Good evening, Professor Young.
Good evening, good morning. I'm here. Thank you.
Okay, thank you. So before I give the time to Professor Tony Young, I would read a short CV of him. Could the committee present the CV? Okay. So Professor Tony Young is professor at the University of British Columbia, Canada. His expertise is in structural and earthquake engineering. He obtained doctoral degree from University of California in 2006, and he has several publications. The recent one of them is Collapse Probability of Existing Concrete Buildings, the Evolution of Seismic Rehabilitation, and also many other publications. And he received also several awards. In 2020, he received EGBC Meritorious Achievement Awards from Engineers and Geoscientists, British Columbia, Canada. And also in 2019, he received awards, Technological Award from New Zealand Concrete Society, New Zealand. And also in the same year, he received award, Sandy Cormack Award from New Zealand Concrete Society. Okay, I think that's a short CV from Professor Young. So Professor Young, I think I will give the stage to you. Your time is up to 9:35. So the time is yours.
Wonderful, wonderful. Let me see how I share my screen. Let's see if I can share my screen. Perfect.
Professor Young, we couldn't hear your voice.
Can you hear me now?
Could the committee check?
Now?
Not really clear from
Can you hear me
here.
now? Can you hear me now?
Still not very clear from here.
Let's see. If I can get closer to the mic, maybe.
Oh, that's better. Yeah, that's better.
Very good.
Okay, you could start your presentation. Yeah.
Very good. First of all, is my screen shared? Let me see. Can you see my screen?
Yes.
Yes. Okay. So it's in the. Okay.
That's good.
I think the slide is in the wrong one. Let me just. Okay. Very good. So I think you can see my screen. So very good. So I get started right away. And thank you so much, Professor Afriyadi. Good morning, everybody. My name is Tony Young. It's truly my pleasure to have the opportunity of presenting again at the International Conference on Earthquake Engineering and Disaster Mitigation. And Selama bagi all my friends from Indonesia. Okay, so let me get started with today's presentation. Today I'm presenting a presentation showing the future of earthquake engineering and structural engineering technology with the title of Next Generation Smart, Carbon Neutral, and Resilient Infrastructure. My first slide over here shows, is any delay on my screen or no? I'm not 100% sure.
Still, we couldn't see your presentation, I guess.
You are not seeing my presentation?
No, still in the same page.
Okay. Allow me to stop sharing, and then I will share it again. Just 1 second. Okay, how do I do that? Just 1 second, my apology. Okay. That's a good question. I have stopped sharing, so I'm going to try to share my screen again.
Yeah, it's right. Yeah.
Okay. Is my screen shared now?
Oh, yeah, yeah.
Okay,
it's,
very good. Very good. Okay, so I will start with animation mode, and please do let me know if it's shared properly. Okay, so this slide shows.
Okay.
Very good. This slide shows things very fast. Right now, it's 2020. Our global population is about 8.3 billion people. We're expected by 2050, so about 20 years later, 20 plus years later, the population will grow to 9.7 billion people. And these are the data presented by United Nations. So this increasing amount of population we are seeing started showing rapid urbanization worldwide. I think there are some delay to the presentation. Professor Afriyadi, I'm not too sure because it seems the presentation is not running. Professor Afriyadi, I'm going to turn off my screen. And
Yeah,
maybe
this-
it's
the screen.
okay, very good. So I can see what you see. So it's a bit delay. I don't know why, but it's okay. Let me continue with that then. So you can clearly see there are rapid urbanization worldwide, and this is a picture in New York. Okay, so you can see big, dense population. This is a picture of Toronto. There will be some delay, and I don't know why. I can see my screen change here, and I think on your side is still showing New York, right? Yeah, okay, I can see now. Are you seeing Toronto now? Very good, no worry. So this is a picture of Toronto, and this is a picture of Vancouver. My apology, I'm actually seeing what you're seeing, so it's a bit delayed in terms of the speed. Professor Adriani, I'm not sure, is it from the internet, from your side, or too many people on Zoom? Whatever I'm sharing, it is not immediately shared with you. Not sure why. Are you still seeing the picture of Toronto?
Yeah, I could see the city and also the beach.
Yeah, so it's very strange. Oh, you can see the city with the bridge. Okay, so this is Vancouver then, finally. So you can see with so much population growth worldwide, we're expecting to see a lot of new infrastructure need to be built. It is expected about 2.1 trillion square feet of new construction need to be built by 2050. So for many of us, we don't really use the unit of trillion square feet. Just so you know, Jakarta is about 800 square meter, okay, a kilometer, 800 square kilometer. Singapore about 700 kilometers square. So 2.1 trillion square feet means is that we need to rebuild or build 9 Singapore every year around the world for the next 30 years. So there are a lot of construction need to be built. And these constructions are creating global warming worldwide. I'm going to pause a little bit because it seems like the presentation slide showing up in your conference is slow by a few seconds. I don't know why. I think you're still seeing a picture with City of Vancouver, right?
It's already changed to, yeah.
You can see it now. So now you can see the whole world are seeing a huge carbon emission growth. So you can see United States, China, actually Indonesia in high production of carbon emissions. These carbon emissions are causing global warming and it's causing an issue. We see forest fire, we see a rise in seawater levels. So many countries have decided to work together in achieving green carbon gas emission net zero by 2050. Okay? In order for us to achieve net zero by 2050, what we need to do is by year 2030, we needed to start cutting the carbon emission by 30%. If we don't do that, part of Indonesia will be undue. In addition to the new build, in addition to the carbon impact caused by the war, we are seeing our existing infrastructure in North America are deteriorating very fast. Right now, based on our initial search, it costs about 141 billion Canadian dollars to actually replace existing infrastructures which are rated very poor. We cannot reuse them again. And we need another injection of $11 trillion new population growth. In addition to this population growth and maintaining of the infrastructure, we're also seeing our infrastructure experiencing lots of loss, financial losses through natural disaster, earthquake, windstorm, fire, flood. We see all the time. Within the period between 1998 to 2017, less than 20 years, globally, the economic loss for infrastructure reached about close to $3 trillion US. So the next generation infrastructure that we're focusing on developing, we started using new way of construction. So we pre-made those in a factory and quickly assemble on site. We're developing 3D printing technology to allow us. We're reusing recycled material, use of a massive timber material to reduce the carbon intent to the new infrastructure. Of course, at the same time, we want to make sure those infrastructures have all the technology we can to make sure they are safe for the next round of earthquake. So we start developing energy dissipation devices. Finally, we're using monitor in real time, so the next generation infrastructures are smarter, they are carbon neutral, and they are resilient. Back to the pictures we see, the conventional constructions, this is the picture in United States, but no different in many other places. We lack of skilled workers. In North America, we have very, very few skilled workers are working anymore. We also, conventional construction needed a lot of time for construction. And you have a lot of waste in the construction material, and a lot of time, very poor quality assurance. And many times it's affected by the weather and lack of construction site for us to build. So over the last 20 plus years, the world start developing newer way of building faster to meet the global demand. This is a video showing you the technology design and assemble the structures together. This is a real line time showing how fast construction can be built. This is a 15-story building within 2 days, less than 2 days, 46 hours, the building are able to construct all the structural and non-structural components are assembled. The lights are turned on, the water is running, the furniture are put in. So within 6 days, less than 7 days, we have a brand new 15-story hotel that we can use. This kind of new technology are being heavily investigated around the world. In fact, in China, they are thinking of building the next tallest building in the world, 220-story, using fast construction technology. Right now, in China, for the modular construction technology, if you don't use it, you may not be able to get a permit to build in a city like Shanghai or Beijing. So in North America, we're developing a fast construction technology. Buckling restraint knee brace truss movement frame is one of the technology that we have collaborated with our colleagues around the world. So the idea of it is using truss that you can use this in regions to create large interior spacing. To ensure it's performing well for earthquake, we started developing energy dissipation devices to dissipate energy. And we have secondary devices to dissipate additional energy. So in the laboratory, we tested many of those devices that we developed, and we're working with Star Seismic, now called Brace, to developing those damper technology. And we developed simulation model to demonstrate that the structure can actually work well and very well during storm and earthquake shaking. So the device can yield and dissipate the energy throughout strong earthquake shaking. After it's done in the numerical simulation and experimental testing, we then the structural system will be placed. All the electrical, mechanical, and plumbing system are put in the factory. We put in the floor, the fire coating, sound insulation, and fire coating on top, and then we can easily ship to the site. On site, we can quickly place, using very limited amount of crane and humans, then we can place those columns and lift the floor to place and make sure it works for high seismic zone like Indonesia and in Vancouver. We started putting these energy dissipation devices. The device can be very quickly, the structure system can be very quickly constructed using very limited amount of human. And the system, it's very lightweight, very fast construction, and is earthquake resilient. So we can easily deploy it to many locations around the world. The system can be placed in groups of modules and places together, and we can create a very large opening spaces, no different than this rendering shown on the slides. The other technology that we have developed here in North America is reusing the shipping container technology to build housing, because we have many shipping containers left in the North Shore, and then we needed to reuse them. And our goal is to quickly assemble them so we can solving the housing issues in Vancouver. So we put the shipping container in the factory. We put in the electrical, mechanical, the kitchen into the module, and we quickly ship into the site. To make sure it works for high seismic, put the modules on top of each other. And we developed the special bonding mechanism between the modules very, very fast without waiting for the concrete to cure. Those panels very easily inside those individual units. They are furnished kitchens with cabinet, water, everything is running. So this is the type of construction that we can quickly addressing the housing market. Very recently, just like Indonesia, Vancouver, Canada, Canada in general, have abundant resources of wood. Okay, Canada and Indonesia are both countries exporting woods for resources. Very recently, we started developing high-rise buildings using timber construction. So we started engineering the timber, putting into cross-laminated timber, so we can start reaching to new heights. This is one of the tall 18-story timber building that we built here at the UBC campus. This is another project in Canada. So the idea of another technology that we're doing is start developing these timber glulam columns. We can create a floor system which we can easily manufacture, very light, to bring it to site, and we can assemble them. After we do all system into the slots which pre-located, once one floor is done, we started going to the second floor and continue. In terms of the interior finish, we started developing volumetric modules that we can quickly insert building and then start with another floor system and continue and finishing our high-rise construction. Very recently, on this particular conference, we presented the design of the system, which uses a CLT, a cross-laminated centering conical friction damper, which we developed here at UBC, which is damage-free earthquake, and you will center after an earthquake done. So it provided very nice, stable energy hysteresis. At the base, in Vancouver, we started using a lot of this pin base because our architect liked those design. We reused them in our design. Here shows some very high-level views of the final design we do. We then develop computer models to it using OpenSeas, something that we static and nonlinear dynamic analysis. In the nonlinear static analysis, we do a nonlinear static pushover, so the structure will actually deform, and the energy dissipation devices will pick up the forces. If continue loading, then the devices will slide through the friction devices and dissipate energy. If the earthquake returned, then the devices will actually have a self-centering force to bring the building back to straight without repair required. So after we did the nonlinear static pushover, cyclic pushover analysis, we then do nonlinear dynamic analysis, and we do lots of time history analysis using incremental dynamic analysis procedure. We select a whole bunch of ground motions suitable for the particular site, which is in Vancouver. And the time history analysis demonstrated the energy dissipation device was able to dissipate energy and come back plumb without any residual displacement. And from the large array of nonlinear incremental dynamic analysis, we started pushing and increasing the level of shaking until the structure reaches yielding in one of the devices that we do not allow the failure mode. By doing so, we can quantify the performance of the building using probability of collapse. In that situation, it's actually not collapse. This is a failure probability. Based on the study that we show, the structure has a collapse margin ratio about 1.79. So what it means is that about 50% of its capacity, 50% of the time, the median capacity is actually about 1.8 times its design level. If you accounted for the spectral shift factor, the adjustable collapse margin ratio is about 2.27. So very, very robust. Compared to the acceptable collapse margin ratio, this superior system actually performed very well according to the North American Code. Very recently, with advancement of AI technology, we started working very heavily into making this kind of new structure system be built using robotic technology. We started developing virtual reality technology, building information technology, robotic construction technology and digital twin technology to allow us to make those buildings without much human intervention. So we are starting doing the structural design, but now we have integrated with our virtual reality model, so we can actually see everything before it's being built, and we are developing our robotic technology to assemble those systems. Yeah. So now let me give you some quick summary and conclusion. Next are being developed, and we're making the next generation structures lower initial cost, faster to build, higher performance, smarter, and environmental friendly. I'm very sure, together with our colleagues in Indonesia and around the world, I'm sure we can make a significant difference. With that, I would like to thank you for your attention and look forward to have the opportunity to welcome you all to beautiful British Columbia, Vancouver, and hopefully have the opportunity to re-meet my close friends in Indonesia again very soon. Thank you, Professor Afriyadi. I'm done with the presentation.
Thank you. Let's give applause to Professor Yang. Is it possible to have one or two questions, Professor Yang? Oh.
Thank you. Yeah, I'm here. Absolutely.
Okay. The audience, if you have one question that will be delivered to Professor Yang, could you please raise your hand? No, Professor Yang. So in your presentation, you present that you developed the sub-center canonical damper for timber buildings. Is it possible also that damper is applied to other types of buildings like concrete that may be heavier than timber? That possible?
Yes, Professor Afriyadi, you are thinking correctly. Actually, those dampers are developed originally for concrete core wall, and we have already built some testing for it, and now we are only applying for this CLT shear wall. So yes, you can apply it to other type of system.
Okay, thank you. There is one thing, participant that will raise the question
Sure.
from the Zoom meeting. So could you please tell your name and then? Okay, go on.
Okay. Thank you for the opportunity. Actually, I'm really impressed with your presentation from Professor Tony Yang. I want to ask about your opinion. I've heard about the high-rise building in Helsinki, Finlandia, where all the materials is from wood.
Hello. Could you? Your voice is not very clear from here. Could you? I'm not sure whether Professor Yang can hear clearly.
It's not clear to me too.
Yeah, not very clear. Could you?
How about now? Can you hear my voice clearly?
Stephen, if you possible, can you type it in the chat? Maybe I can answer it, and I can repeat your question.
Okay. I want to ask about your opinion about the high-rise building in Helsinki, Finlandia, where all the materials are from wood.
Steve,
Is it possible?
I didn't hear that very clearly. I heard about high-rise building and can you repeat again?
I want to ask about your opinion about high-rise building in Helsinki, Finlandia, where all the materials are from wood.
Can you type it?
The high-rise building in Finlandia, and what is the problem?
All the materials are from wood.
Professor Afriyadi, did you hear that? I didn't understand the question.
Not very clear actually. So maybe could you write your question on the chat? Maybe I have to come forward. Sorry.
Don't worry. It's already very amazing. I'm sitting across the ocean and we can talk. Very good. Yeah.
Can you write your question on the chat?
Yes. Wait a minute.
Not yet.
Materials.
Ada. Oh yes, I want to ask about high-rise building in Helsinki, Finlandia, where all the material are from wood.
Okay, so what's the
Maybe you
question?
can read also from the chat. But the question is, I want to ask about high-rise buildings in Helsinki, Finlandia, where all the material are from wood.
Yeah, but what's your question? Are you saying that it's possible, or what's that question mean? So my opinion, whether it's a
You just give your opinion about the high-rise buildings in Helsinki.
Okay. Steven, I'm not familiar with this particular building you're talking about, but right now in North America, we are building high-rise building all in wood.
Yes.
So right now we already built one here in my campus, 18-story, and we're pushing into 20 plus stories. So the technology is available, and we are already making them to go to high-rise. Is that your question?
Yes, I think, I think you have another question. Okay, thank you, Professor Yang.
Okay.
There is one other question, if possible, from Professor Bambang Sendro. Please, Professor Bambang Sendro.
Okay, thank you. Good evening, Professor Yang. Thank you very much. It was very, very great presentation and also innovation. My question is very short. Suppose we develop such kind of innovation in designing and building the new generation of building. What about the I mean, in many countries we have code, design codes. We have also construction guideline that we have to follow. So how to initiate those situation? Suppose in Vancouver you start to build this kind of innovative building.
Correct.
Do you need any permission or the permission from a kind of peer review or something like that at every region that you want to build your creative building? Thank you very much.
Thank you, Professor. Okay, Professor Yang, you could answer.
Yeah, Professor Suhendra, thank you for the good questions. We are pushing on the boundary of the technology, and every time a new technology being made, it's always creating challenging in the way we implemented them. So in North America, what we have been doing is that we do peer review for this kind of structure system. And the peer review will require experts like yourself or myself who are expert in the material level, in the structural level, and in the ground motion level, and then on the modeling. So that a group of peer reviewer will review projects like this. As a matter of fact, in America, United States, almost all buildings, even is made with the traditional technology, we are all going through peer review these days because it all break the high limit what the code is doing right now. But I believe that's where the future is going, where the building code stop giving you detailed guideline how every building need to be designed. It will give you targeted performance, how the building need to achieve and you as an engineer, and there are many great engineers around the world, are able to design the building to achieve the performance they want. And hence, we are moving towards this performance-based goal of a new structural system. I hope that answers your question.
Okay, thank you. I think you have
Thank you.
answered the question very well. I think because of time, so we have to finish this session. So I think let's give a big applause to Professor Yang. But before Professor Yang leave, I think certificate of appreciation, digital certificate appreciation.
Thank you. Highly appreciate it. Thank you so much. Thank you.
Okay, again, thank you for your interesting presentation. Although in the beginning we have problem, but this is really very interesting. Thank you again, Professor Yang.
Thank you, everybody.
Thank you for your time.
Look forward to seeing you. Bye-bye. Thank you.
Okay, thank you. Bye-bye. Okay, ladies and gentlemen, we will continue to the second keynote speaker. So the Tanaka. So Professor Hitoshi Tanaka,
yes,
is professor in Tohoku University. His expertise is coastal engineering, hydraulic engineering, environmental hydraulics, and he obtained his PhD in 1984 from Tohoku University. He has several publications. The recent one of them is The Necessity of Using a Wave Friction Factor in Tsunami Numerical Simulation. And he has also received award from APD Distinguished Membership Award at IAHR in 2016. Professor Hitoshi Tanaka, have you joined the meeting? Okay. Could you check the presentation maybe before I give you? This.
Thank you very much, Professor Piadi. Can you hear me?
Yeah.
Okay, so let me share my PPT file. Probably you can see my PPT file. Still take some time. Hello?
Yeah, it's that we have delay here.
Delay. Okay.
Yeah, I guess. Yeah. Okay.
Still take some time.
I can see your slide.
Yeah. Okay. So, thank you very much, Professor Yon Afiadi, for your kind introduction of myself. And first of all, I'd like to express my appreciation for your kind invitation to this international conference. Sorry for being unable to attend the conference face-to-face. I'll make my presentation online. And my topic today is a bit related to a presentation by Professor Tony Yang, energy dissipation. But my talk today is related to tsunami energy dissipation by bottom friction. It is not related to structure. Okay? And as you all remember, we had a very serious tsunami disaster in the year of 2011, as you can see on this slide. And a very important thing is the very black color of the overflowing water, indicating a very big amount of sediment transport by tsunami waves. And similar phenomena happened in your country as well, or during the 2004 Indian Ocean tsunami. Well, okay. This is indicating the importance of prediction of tsunami-induced morphology change. Right? The tsunami simulation has been widely applied in many places, even for practical designing already. But for sediment transport modeling, still there's so many things to be clarified. Right? And this is showing the flowchart of sediment transport calculation and also resultant coastal morphology changes. From tsunami numerical simulation, it is possible to evaluate flow velocity and also water level variation. And from this numerical model, we can obtain the bed shear stress from the numerical model. And for tsunami numerical simulation, we normally use the shallow water equation, which is valid for long wave, long period wave. And there's a very, very clear demarcation between the short period wave and the long period wave, as you can see in this diagram. And when we apply the numerical model, we simply assume that it is long period wave. So flow phenomena must be similar to steady flow. Okay, steady flow friction factor can be applied. But according to our recent study, this demarcation, right? The demarcation in the friction law is not valid. According to a study, even under long wave friction factor should be utilized instead of steady friction factor like Manning's N or Sergi N, whatever. And according to our recent study, boundary development and the tsunami is highly influenced by the unsteadiness. It is very, very different from steady current. And therefore, the steady friction law is not always valid. In some situations under tsunami, even if we can use the shallow water equations, the steady
Professor Tanaka, it seems that